Welcome to the course Business Analytics and Data Mining Modeling using R Part 2. So, in previous few lectures we have been discussing cluster analysis. So, in previous lecture specifically we stopped at the point where we did a small exercise in R and applied cluster analysis on full data set. We applied what's approach, single linkage and average linkage, and we saw how the model results can be easily understood from dendrograms. We also saw if we have a number of if we have a number of desired clusters that we want to create, then how that is possible in R, and using dendrogram how that is easily how that can be done. We also saw that in that process each of those clusters and the observations that are going to be part of those clusters can be clearly seen from the dendrogram. So, now let us continue our discussion on cluster analysis. So, specifically HAC methods that we have discussed so far. So, one thing that you would notice in this that all these methods, HAC methods that we have discussed so far, they produce clusters which are nested. So, that was clearly seen in the dendrograms as well. Now, we can also see that we can see that in the dendrogram when we decrease the number of desired clusters, then we can clearly see the nestedness of those clusters. So, that was clearly seen in the previous lecture. Now, many clustering applications actually value this property, the nesting of nesting of clusters. So, one example is taxonomy of living organisms. So, any particular application where we are creating categories and then subcategories and then subcategories, any kind of problem where we are looking to group things or cluster things into these kind of nested forms, right, where something is going to be a part of something, and then if we are looking for certain themes in a particular domain, if we are looking for classify certain things in a particular domain, trying to create taxonomy. So, this particular property, this nested cluster property that we get from HAC method, this is going to be quite useful. Now, let us talk a bit about the usefulness of cluster analysis results. So, in the previous lectures we applied a few approaches under HAC, and we saw that the resulting dendrogram was slightly different the way it happened, and there were some variation in the results, right. Few things were common. For example, singleton clusters were quite the same in almost all the approaches. However, some other observations so there was a bit change there depending on the approach. So, how do we ensure the creation of insightful and meaningful clusters? So, we are going to discuss few points which are going to be useful, which are going to be helpful in terms of creating meaningful and insightful clusters. So, cluster interpretability, this is one important thing for creating insightful and meaningful cluster. Whether the clusters that you have produced, whether they are whether they can be interpreted, whether they can be understood the way they are. So, we can explore some of the characteristics of each of these produced clusters and try to understand try to interpret those clusters, what they signify, right. So, all those things can be explored. So, for example, summary statistics is one. So, we can look at the summary statistics of each of those clusters and try to identify how those clusters are different, whether there is a defining characteristic which is different, which are creating those differences. So, those things we can identify, and that will give us a sense in terms of interpreting those clusters. We can also look to identify a common feature across clusters. Sometimes this is also possible, that for example, if we are applying cluster analysis on customer segmentation. We are trying to create customer segments which could be later on used for our marketing and promotion exercises. Then in that case, sometimes it might so happen that the clustering results might tell you that these customers, the common feature that you can see is the might be the geography or the region, right. So, some customers, even though we might have clustered them using a number of demographic and other variables, but eventually when the clusters are formed, we might be able to see that there is a cluster of customers belonging to metro cities. Then there could be clusters of customers belonging to tier 1, tier 2, tier 3 cities. So, geographic the common feature might be clearly visible. So, we can always look for these kind of common features. Summary statistics is always going to be useful, and based on what we learn from some of these things, we can start labeling these clusters. So, once we start labeling these clusters, our cluster interpretation would be much more meaningful and insightful. Few other things that could be done, for example, we can check the cluster stability. So, if input changes, if some of the observations change in the data set, so whether the clusters that were formed, they change significantly, or they are stable or robust enough to addition or deletion of points. So, those kind of checks can also be done. We can always look whether the produced clusters, they are robust enough or stable enough for input or data changes. Now, another way to check cluster stability could be partitioning followed by clustering. So, we can partition the cluster and then it can be followed up with the clustering. So, we will get the clusters, then the clusters would be created using one particular partition, and the other partition could be used to test these clusters, right. So, we can compare how the cluster assignment happened in the partition on which clustering was done, and in the remaining partition where it was applied. So, we can compare that and see whether the cluster formation that we did, whether that was stable enough or robust enough. So, this approach can also be used. Another thing that could be done is the cluster separation, whether the clusters they are separated with each other in a reasonable fashion. So, that can also be checked. So, for this we can use this particular measure, this particular metric, ratio of between cluster variation to within cluster variation. So, this particular value will also give us a sense, a idea about how the clusters are separated from each other. So, if this value is on the higher side, then probably the clusters are separated reasonably. If the value is on the lower side, then there might be the separation, the cluster separation might be a problem. So, these are some of the points: cluster interpretability, cluster stability or robustness, and the cluster separation. So, these are some of the things that can be analyzed, and then we can arrive at whether the produced clusters they provide us, they are going to give us some meaningful or insightful findings. To talk about HAC and to summarize a few more comments on HAC, now we can see that purely HAC being a purely data driven technique, in the sense that we do not even have to specify the number of desired clusters. The process is applied, and depending on the number of clusters that we want, we can later on decide using the dendrogram, and we have seen this process. So, the whole thing is whole approach is quite data driven. So, clustering process and results depicted using dendrogram, so that we have seen. So, we can using dendrogram it is easier to understand and interpret. So, these are some of the plus points of this approach. High memory and computational intensity. So, this is one drawback of this particular approach, HAC approaches, because if you remember in the R itself, we were creating all the time, we were creating this distance matrix, and these distance matrix were of the size n cross n, where n is the number of observations. So because of this, the lot of storage requirement for implementing this approach, and that would also slow up the processing. So computational intensity would also be on the higher side because of all this storage that we require for distance matrix computation, and the later steps also would require, because of this they would also require more computational time. So this is one drawback. So the technique overall might be slow. Then the next limitation of this particular technique is the major drawback, where we just do one pass through the data. The way whole clustering process pans out in HAC, we just go through the data once, right. So what happens is, if some premature allocation of records, premature allocation of observations to clusters, if that thing happens, then we are not left with any scope for revision. So it is just in one go, one pass through the data, and we get the clusters. Depending on the number of clusters we can always pick, but that result is out and there is no scope for revision. So if any premature allocation happens, so we cannot do anything with it. So this is one limitation of HAC. Few other limitations, for example, sensitive to data changes. If input data, if few observations are dropped or added, then of course the way clusters are produced, that can change. So sensitive to data changes. Outliers, sensitive to outliers. So few outliers can also determine in a way the clustering clusters are produced. Distance matrix. So if we change the distance matrix, as we saw that dendrograms that we produced, they were slightly different, but that is just for the distance computation between clusters. If we look at the distance computation between 2 points, between 2 observation or any other points, for example, typically we use Euclidean. So if we change this distance matrix from Euclidean to something else, then also the results might change. So for example, average linkage, that is something where the high chance of results changing is going to be there, because the way average linkage, the way distances are finally computed, if we change the metric, so those values are also going to be changed. So it is more likely that the results are also going to change. So in single and complete linkage, they are slightly robust to changes in distance metric, in the sense that they rely in the relative ordering. So as we talked about in the previous lecture, so if relative ordering, if we change the distance metric from Euclidean to something else, if this relative ordering remains same, then the results of single and complete linkage typically going to be might remain same. However, if this relative ordering is disturbed because of this change in the distance metric, then of course the results for even single and complete linkage might also change. So there is going to be a lot of variation in HAC methods, the kind of results. We change the approach, results might change. We add, delete few observations, the results might change. Of course it is sensitive to outliers, and as we discussed that if we change the distance metric, then also results might change. So these are some of the limitations that are there for the HAC approaches. So this brings us to our next part, that is non-hierarchical methods. So as we have discussed in previous lectures, that non-hierarchical methods are slightly different from hierarchical methods, but in the very first step that we require is the number of desired clusters, they are to be pre-specified. So we should have some kind of idea about the number of clusters that we require, and that this particular number is to be specified. Now what happens in non-hierarchical methods is that after this, once we know that this is the number of clusters that we want, each observation is assigned to one of these clusters such that dispersion within clusters is minimized. So, this is one major difference from what we have discussed in HAC approaches. So, each observation, so there in HAC we were looking to identify the closest observations and we were merging there, but if we look at the non hierarchical methods, the observation is assigned based on the minimization of dispersion within cluster dispersion. So, what happens is it leads to homogeneous and non overlapping clusters. Now, typically the more popular and common measure of within cluster dispersion is this: sum of distances of observations from their cluster centroid. So, if Euclidean distance metric is used, then it can become sum of squared Euclidean distances of observations from their cluster centroid. So, you can see from the measure itself that all the the observations they are being measured from their centroid, the cluster centroid, and the dispersion is being computed. And now the way observation is assigned in such a fashion that this dispersion, this particular value is minimized. So, if we look at the whole the overall formulation of this approach, non-hierarchical approach. So, this approach can be framed as an optimization problem using integer programming. However, as we know that integer programming with so many with a number of variables and with a large data set where we might be having in large number of observations. So, it might be computationally intensive, because the integer programming will actually look for compute for the optimal solution, and that might take a more time. So, that is not desirable. So, what we can do is we can opt for a fast heuristic method which can produce good results, if not the optimal one. So, we are not guaranteed with the with producing the optimal results, but the method can actually give us a good result in a short time, right. So, one such method is k-means algorithm. So, which is something that we are going to discuss next. So, in non-hierarchical methods, this is the algorithm that we are going to cover, k-means clustering. So, let us start our discussion on the algorithm, and we will also see how it is different from what we discussed in HAC. So, the very first step, we start with user specified number of desired clusters. As I talked about, one difference between hierarchical clustering method and non-hierarchical clustering method is that in the non-hierarchical you have to specify the number of desired clusters, but in hierarchical cluster method everything is part of the process. So, the first step is we start with user specified number of desired clusters, that is k, and that is how the name comes there, k means clustering. Now, once we know the number of desired clusters, then we have to do some initial assignment of observation into these k clusters, right. So, this initial assignment will become the basis for implementing next steps of this particular algorithm. Now, once this initial assignment has been done, we can compute the cluster centroids, because now each observation is going to be part of some cluster as per the initial assignment. Now, we can go ahead and compute the cluster centroid. Once this is done, we reach to our step number 2. So, in this step each observation is now reassigned to the cluster with nearest centroid. So, now all the observations they have been initialized to one of the k clusters, and then we compute the cluster centroid, and then each observation can again be reassigned. So, we can compute for each observation, we can compute its distance from each of those k clusters and find out which particular centroid is closest to the observation, and then reassign this observation to that particular cluster. in this fashion, some of the observations, some clusters might lose some observation and might gain some observation, and this might happen to all the k clusters. So, this process will happen. So, this reassignment will result in a lot of gains and loss of observation from each of those clusters. So, what we need to do is we need to recompute in our third steps. In our third step, we can see recomputation of cluster centroids to adjust for the loss or gain of observation. So, we will have to recompute these cluster centroid, and once this is done, we can again go back to step number 2 and then step number 3. So, we can keep on doing this till new iterations lead to decrease in cluster dispersion. So, as we talked about, the metric that is used is we look to minimize the within cluster dispersion in this process, in this whole process, k-means process, and in general non-hierarchical approaches as well. So, step 2 and 3, they are going to be repeated till the time the within cluster dispersion it keeps on decreasing. Once saturation is reached, once we can no further decrease this dispersion, then we will stop. So, let us go back to R Studio and we will go through an exercise in R to understand this k-means clustering process in more detail. So, as you can see here, we are going to start our this part of cluster analysis, k-means clustering. So, again let us reconsider the data set. So, this data set for breakfast cereals was about 35 observations that we had in total. We can recheck this from the environment section. So, we had 35 observations and 14 variables. So, we can see this DFN 35 observation and 14 variables. So, within this, if we just consider the first 5 cereals like we did in HAC. So, in this example, we are going to consider just first 5 of these 35 observations, and we will also pick just we will also consider just 2 variables, rating and price. So, let us consider that first 2 cereals are part of one cluster, that is cluster A, HPC and HBC, a similar exercise like we did in HAC. So, next 3 cereals let us assume they are part of cluster B. So, these cereals are SK, MH, CC and CD. So, centroids for these 2 clusters we have computed before as well. So, let us get that let us see that data again. So, if we run this, so these are the centroids, these are the cluster centroid, one for cluster A. So, row 1 is for cluster A, centroid for cluster A, row 2 is centroid for cluster B. We can see just 2 variables are being considered, rating and price, and that too normalized scale. Now, as we talked about, we know the cluster centroid and we have these 5 observations. Now, we will compute a distance metric which will have distances between these 5 observations and each of the cluster centroid, because we want to identify that each of these observation and their closeness with 2 cluster centroids that we have. So, this will actually give us a 5 cross 2 matrix. So, we will have to initialize this. So, this is the 5 cross 2 matrix that we are going to initialize. The names are this. So, names are these abbreviation of these serials. So, let us run this code, and then in the column side we have 2 centroids, centroid A and centroid B. So, these values, let us compute these distance values. So, you can see we have a for loop here where we are using the dist function, and in this we are using this df2 data frame which has the normalized scales for our 2 variables, that is rating and price. Now, using the observations, using the coordinates of these 5 observations and then the coordinates of centroids, we are trying to compute the distances between these points. So, this for loop will give us these distances. So, you can see method has been specified as Euclidean. So, let us run this loop. So, what we get in the output is in the row side we have these 5 serials, and for each of these serials we can see the distances from centroid A and centroid B. So, this can be clearly seen. So, for example, HPC, its distance from centroid A is 0.7625492 and its distance from centroid B is 0.762574. This is quite close. So, this particular observation is in a way equidistant from both the cluster centroids A and B. If we look at the second observation HBC, so this is closer to cluster A and also part of cluster A. So, HPC, let me clear this. HPC initially as it it was part of cluster A. However, we can see from this data that it is in a way equidistant from both the centroids, but HBC, it is quite clearly it was part of cluster A and closer to cluster A as well. It is quite far from centroid B. Then third observation SKMH. So, clearly we can see this is closer to its own cluster centroid. CC is also closer to its own cluster centroid. CD is also closer to its own cluster centroid. So, from this output we can see that last 3 observations, last 3 serials are closer to their own cluster centroids, and HBC is the second one is closer to its own cluster centroid. But if we look at the first observation, though it seems to be distant from both the cluster centroids, but if we closely look at the these values up to 7 decimal points, we can see that HPC is much closer to centroid B. So, therefore, it can be reassigned to cluster B. So, this is what is going to happen as per the algorithm that we will find out for each observation, and its closeness with each of the cluster centroids. So, we can see HPC has to be reassigned as per this algorithm, k-means clustering algorithm, has to be reassigned to cluster B. So, the same thing we have noted here in the comment section. Reassignment of records. Now, cluster A would be left with just one record, that is HBC, and cluster B will gain a record, that is HPC. So, earlier it had 3 records, now it will have one more. So, in total it will have 4 observations in total, and the cluster A would be left with just one observation. So, cluster A would be a singleton cluster, and cluster B would have 4 observations now. So, now let us reconfigure our data set for these 5 observations. So, now here in this data frame we can see we had done some reordering of observation. So, now the observation belonging to the only observation belonging to cluster A, that is HBC, comes first, and the remaining 4 observation belong to cluster B. So, just one observation belonging to cluster A and the remaining 4 observation belonging to cluster B. Now, what we can do is we can again recompute the cluster centroid. So, this is as per the algorithm that we have discussed. We are going to recompute the new cluster centroid. So, here again you can see in the code for the first cluster we have just one observation. So, the mean values that we have to compute for each of the variables just one one observation. So, therefore, the mean value is also going to be the value of that observation. So, the centroid for cluster A is going to be that single observation itself, but centroid for cluster B is now going to be slightly different. So, in this we can see the second one 2 to 5 here. The centroid for second cluster B, 4 observations are involved, and the mean values are being computed for each of these variables. So, let us run this code. Now, we can see the centroids for each of these clusters, cluster A and cluster B. Now with this now we have the new cluster centroid. Now what we can do is, again we can go back to step 2 that we talked about in the algorithm. Now again we can compute a distance matrix which will have distances between these 5 observation and each of the new cluster centroids. So now again we are going to compute a 5 cross 2 matrix which will have all the distances that we need. So let us initialize this. Row names, you can see some change, right. First observation belonging to cluster A, then followed by 4 observations belonging to cluster B. So let us change the row names and the column names, centroid A and B. Now we have this for loop which is going to compute for us the Euclidean distances between these 5 observation and these new centroids. So let us run this code. So we can see from here that now HBC, the first observation, this is the centroid, its distance from centroid A is 0 because this observation itself has become the centroid for cluster A, being just the one observation in that cluster. Now we can see HPC clearly its distance from its own cluster, that is B, is smaller. For SKMH, its distance from its own cluster is smaller. CC, its distance from its own cluster is smaller, and similarly for the last one, CD. So no further reassignment is required. So this is the final cluster formation. So first observation HBC goes to cluster A and the remaining 4 observation go to the cluster B. So this is the final formation. So we have gone through the k-means clustering using this particular small just 5 observation. So we will stop here and we will continue our discussion on k-means clustering in the next lecture. Thank you.